moment of inertia of the solid sphere of mass m and radius r about an axis through its center is 2 by 5 mr square, then what would be the moment of inertia about an axis tangential to the surface of the sphere? In fact, we had covered it in the various variations of moment of inertia, right, in the table which we had created yesterday.
Yes.
Let's consider this to be a sphere. Let's say this is the axis which passes through the center of mass of the sphere, right? Suppose if the sphere is going to rotate about this axis, then the moment of inertia is given to be what?
2 by 5 mr square.
Yes. The moment of inertia about an axis passing through center of mass. Is 2 by 5 r square for a solid sphere. Even if this data was not given to you, you needed to remember this, right?
Yes, sir.
All right. Now, what is asked is the moment of inertia about an axis which is tangential to the surface.
Right.
So tangent is a line which touches the sphere, right? Which that just meets the sphere at one point, correct?
Yes, sir.
Suppose if this was the axis, the orange line which I have drawn, if this was the axis, then what would be the moment of inertia? So without mentioning, going into the theorems, right? I told you, if this is the case, if the distance between both these axes is r, then you just need to add to the existing result an mr square yesterday, correct?
Yes, sir. 7 by 5 mr square.
Exactly. So this will be nothing but 2 by 5 mr square plus
mr square.
yes. The answer would be 7 by 5 mr square. Is it clear, Samuel?
Yes, sir.
Yes.
Just writing.
Yeah, make a note of it.
So COM over there represents center of mass, right?
COM represents center of the moment of inertia about an axis passing through center of mass.
Okay, sir. Done, sir.
All right. Okay. There's also a question on center of mass. Okay. The moment of inertia of a uniform circular disk of mass m and radius r about any of its diameters is 1 by 4 mr square. What is the moment of inertia of the disk about an axis passing through its center and normal to the disk? Actually, this question we can answer without any data because this is a standard answer. What is the moment of, even you can consider as an independent question. Yeah, this is something which you need to remember, right, from the table. So all the data which is given in the table needs to be remembered, correct?
Right,
What
sir.
is the moment of inertia of the disk? So let's consider this the disk. About an axis passing through its center. So this is the center of the disk. And perpendicular to its, normal to the disk. Normal means at right angles to the disk.
Right. Yeah.
So if your disk is going to rotate about this axis, then what is going to be the moment of inertia? So this is a standard result for a disk about an axis passing through its center of mass and perpendicular to the disk. The moment of inertia is given by
half mr square.
Standard result. So that will indeed be the answer. All right.
Yes.
But if you want to come, suppose if you did not know this and come from the data that is given, yes. For the time being, let's say, let's consider that, we don't know this answer. We have to come from the data that is given, let's say. Moment of inertia of a uniform disk about any of its diameters is 1/4 mr square, right?
Yes, sir.
Let's say consider this as a circular disk. Now what is given is about a diameter. Let's consider this as a diameter. And the disk is rotating about this axis, okay? This value is given. How much is this?
1/4 mr square.
All right, let me call it as I dash. So one more I had told you in yesterday's class, if you remember, when my friend mentioned this. So if you are given the moment of inertia about an axis passing through center of mass and perpendicular, then if the axis is passing through center of mass, but it is on the plane, on the plane of the disk, then what you do is, whatever this value is, half of it will be this. Yes, if the axis is on the plane of the disk, and it is also passing through center of mass, then the moment of inertia will be half of what it was in the previous case. Therefore, half of half mr square will be what? 1/4 mr square.
Correct.
You just have to, so I dash will be nothing but half of I. That's all. So if this is given, on the plane is given, then if you have to find the one which is normal, you have to double it. That's all. So if you double 1/4 mr square, you will get what?
1/4 mr square means 1/16.
No, not square.
Okay.
Listen to my question.
1/8.
Double it, right?
1/8.
Multiply by 2.
1/8.
1/2 mr square, not 1/8. You're doubling it. See here, from the axis which is perpendicular to the axis which is on the plane, you have to divide.
Okay.
If you are given this and if you are asked this, then you have to multiply by 2.
Right.
So 1/4 is given, 1/4 mr square is given, and you need to find the one which is perpendicular to the axis. So what should you do? Multiply by 2. So did you understand?
Yes.
If I give you this and ask you this, you have to divide by 2. If I give you this and ask you this, then what should you do?
Multiply by 3.
Multiply by 2. Exactly. Anyways, this question was something which you need to know it, even without the data, correct?
Right, sir.
Yes. Is it clear?
Yes, sir.
If the Earth is to suddenly contract to half its present size without any change in its mass, what would be the duration of the new day? Right. Okay, let's say Earth with particular mass m shrinks to half its size without any change in mass. Then what is going to happen to the duration of the day is the question. So Earth can be considered as a solid sphere. All right. Day is determined by the time that Earth takes to rotate once about itself, correct?
Correct, sir.
Yes. We know that it takes around 24 hours to rotate once about its own axis, correct?
Right.
That's why duration of the day is 24 hours.
Correct.
Correct? Okay. Okay, now it shrinks to half its size without any change in mass, which means the mass remains same. Mass was originally capital M. Even after shrinking process, mass is capital M. All right.
Right.
What was the radius? R before shrinking. What do you think will happen to the radius after shrinking?
R/2.
R/2, correct. Because it shrinks to half its size, radius also will become half, correct? Okay.
You think, sir?
Yes.
Sir, for mass for both when the Earth was in normal size and now when it is shrunk, right? Is it still the same?
Yeah. So that is what is mentioned, right? Without any change in mass.
Okay.
Which means the volume has decreased, but mass has not changed. That means density will change.
Right.
Okay, anyways.
Yes.
So now, in this process, right, there has not been any external torque which has been applied, which has changed its right rotational dynamics.
Mhm.
So because there is no external torque applied, since external torque is zero, we can apply law of conservation of angular momentum, if you remember from what we did yesterday.
Right.
If external torque is zero,
Rate of change of angular momentum.
is zero, or L is conserved or constant, which means the initial value of L is same as the final value of L. That means the angular momentum of Earth before shrinking is equal to the angular momentum of Earth after shrinking process. What is the formula for L?
Sorry, sir.
Hmm?
So what did you say?
What is L? What is L? What is the angular momentum formula? Without referring, you must be able to say.
Angular momentum formula L is equal to I omega.
Very good. L is equal
I
to?
omega.
Very good. Very good. Excellent. So this Li, I can write it as, can I write it like this?
Yes. IF omega F.
Right. Very good. Okay. Right. Now, you can consider Earth as a solid sphere. So what do you think will be the moment of inertia of this?
As a solid sphere.
Solid sphere.
2/5 mr squared.
Very good. Very good. Sam. So after it is shrunk, right? Mass still remains the same. So it is 2/5 m. But what has happened to the radius?
It has shrunk R/2, half of the original radius.
So in place of r, I need to substitute r/2.
Whole square.
Yes, very good. So what does this become? Are you getting this?
Yes, sir.
So the moment of inertia after the shrinking process is 2/5 m r square by 4. And earlier it was 2/5 m r square. Is it clear?
Yes.
All right. Now, next. So we'll substitute that here. So in place of I, I will substitute what?
2 by 5 mr squared.
In place of IF, I will substitute
2 by 5 m into r squared by 4.
right. Now, can you tell me what will get cancelled?
2 by 5.
Yes.
And m so
Right.
r squared.
So what are we getting? Omega I is equal to,
Omega f by 4.
right. So this is the angular velocity. All right.
Yes.
Now there are two ways of looking at it. So what is omega f equal to?
Could be equal to 4 omega I.
Correct. So omega refers to what? The speed with which Earth rotates, right?
Right.
Now, has it got faster or has it become slower?
Gone faster.
Right, 4 times faster. Correct.
Yes.
So earlier, if it was taking 24 hours to complete one rotation, now it will take
24 times 1.
huh?
Wait.
It has become faster means it will take less time or more time.
It will take less time.
Correct. How much? How many times lesser?
24 by 4. 6 hours.
6 hours. Is that clear?
Yes.
Directly from here you can answer. Or if you're finding it challenging to answer from here, what you do is you write another formula. The relationship connecting omega and time period. You must have learned it in waves in college. See, omega is equal to 2 pi divided by time. The relationship between omega and time period is what?
2 pi by t.
2 pi by t. You must have seen that earlier. So you can use that. So directly you will get the answer. 2 pi by tf. So we 4 into 2 pi by ti. So what gets cancelled?
2 pi, 2 pi.
Gets cancelled. So you have 1 by tf.
4 by ti.
Ti. Take reciprocal. You'll get tf is equal to
Ti by 4.
what was the initial time period? Initial time taken to complete one rotation?
24 hours.
Yeah, so Ti is 24. So Tf will be 24 divided by 4.
26.
Sorry. 24 divided by 4?
6 hours.
6. Is that clear?
Yes, sir.
All right. A sphere rolls down an inclined plane without slipping. What fraction of its total energy is rotational? A sphere rolls down an inclined plane without slipping. Okay. So we'll understand a couple of words here. First is the word roll, right? Then of course without slipping is quite simple, right? See here, what do you mean by rolling? Rolling is a combination of translational motion and
Rotational motion.
yes. All right. For example, okay, let's say this is the inclined plane. One second. Okay. Let's say this is an inclined plane. All right.
Yes, sir.
Let's say this is an object, maybe a cylinder, whatever, right? Now, just understand here. So if the body is just rotating here, right,
Yeah,
in a fixed position about an axis, so this is called rotational motion, correct?
correct, sir.
If a body is simply, let's say there's a plane, and if the body is simply moving like this,
Right.
what is this called? Translational motion. Linear, correct? Moving in a straight line,
Correct.
correct?
Yeah.
Or this is also called slipping.
Right.
Is that clear?
Yes, sir.
Okay. Now, if a body combines both, it is also rotating and it is moving forward. For example, so what is happening now?
Now, rotational motion is being applied. Rolling.
It is rolling, which means what? It is rotating. At the same time, it is also covering some displacement.
Correct, sir.
Are you able to understand?
Yes.
Yeah. So this is called rolling, right?
Right.
So rolling represents translational motion and rotational motion. So what kind of energy is involved? The kinetic energy is going to be because of translational motion, is also because of what?
Rotational motion.
That we must keep in mind, right?
Right.
So in rolling, the total kinetic energy will be the sum of kinetic energy due to translational motion plus kinetic energy due to rotation. Because the body is performing both, right?
Yes, sir.
Rotating as well as moving forward.
Right.
So this is very important. So now we've seen what is asked here. A sphere rolls down an inclined plane without slipping. Without slipping means it is not moving like this. It is rotating and
Just rotating.
yeah, rotating and moving, right? So it's rolling. It's not slipping.
Correct.
So what fraction of its total energy is rotational? What fraction of its total energy is rotational? Right? So what is asked?
Okay. So we have total kinetic energy,
Correct.
fractional part of it. What fraction of it is rotational?
So what should you find?
Total kinetic energy.
Okay.
After that, find out what fraction of that total energy is rotational. Because
So that
most
means what? You are just reading the statement again for me. What should you find out?
total kinetic energy.
Total kinetic energy you find out. Then what do you do? Don't repeat the question again. Tell me what it means. Let's say you have a fruit diet in the morning, and let's say in the afternoon and night you have, let's say, food or whatever you take, right? Rice or some tiffin. Okay.
Right.
Now I'm asking you, of the total food that you take, what fraction is fruits?
What I consumed in the morning.
Sorry?
What I consumed in the morning. The fruits.
I'll repeat. What fraction of the total consumption is fruits?
1/3.
So what did you do? The amount
You
of
took
fruits consumed divided by total, correct?
right.
So in that sense, right, I'm asking you, what fraction of total energy is rotational? What should you do?
That part of reactor energy is rotation divided by the total kinetic energy.
Repeat. Repeat.
The part of the total kinetic energy, it is rotational divided by total kinetic energy.
No, don't repeat the question again. So what divided by what? Let it be clear, as clear as what you said, right, earlier with fruits and food diet. What should you find? What you should find? What is the ratio that you need to find? Because by repeating the question, you'll be, you can still be unclear about, what you need to do. Very clearly you did, right? Fruits, how much did I consume divided by total food that I consumed, correct or not?
Right.
Then what do you need to do?
Translational plus rotational divided by total kinetic energy.
That will be 1, right? Well, what is the need to find the ratio? Translational plus rotational is kinetic energy only. And you're saying that divided by total kinetic energy. That will be 1, right? What is there to find in it? What fraction of your total food is fruits? What did you do?
I took that part of fruits divided by the total food that I consumed.
Yeah, amount of fruits consumed divided by total, right?
Yeah.
Here, what will you do?
Amount of bar that is rotational divided by the total kinetic energy.
No, why do you say amount of energy just rotates? So tell me clearly, what is it? That's correct. But then, tell me in words, what do you find and, what is it? Because by trying to repeat the question, you will escape the actual answer, what you need to get, correct? You are just finding 3 factors, right? What are you finding?
One is total kinetic energy, translation motion, rotation motion, and total kinetic energy.
The question is all about these 3 things. That's
Right.
all. Now, what you need to give as an answer?
The total kinetic energy, which part of
total kinetic energy, if you give the answer, that should be in joules, right?
Yeah, the part of it is rational. That answer I have to give.
What is the answer I'm asking you? How do you find it? Tell me in,
The rotational energy divided by total kinetic energy.
That's what you have got to right now. Are you clear now?
Yeah.
You understand?
Rotational kinetic energy divided by total kinetic energy is you need to find. Clear?
Yeah.
They have not asked you directly, like, find the fraction of rotational kinetic energy by total kinetic energy. They have just played with English, right? They have just tested your knowledge in English. That's all, right? Yeah. So, but this is what you need to find. Is it clear to you now?
Yes, sir.
Now it's crystal clear. Okay. Go ahead. Now. Okay, ma. Now, what is the formula for kinetic energy, translational kinetic energy?
Half mv squared.
Very good.
Or p squared by 2m.
Yeah.
But
Here
we are
we
doing
here we can maintain this, right? Half mv square.
right.
What about rotational kinetic energy formula? Like this, answer must come.
Half half I omega squared.
Excellent. Good. Okay, ma. So half mv square plus half I omega square. Is it clear?
Yes, sir.
Okay. Now, when I say sphere, if nothing is mentioned about the sphere, whether it's solid sphere or hollow sphere, I recommend you take it as solid sphere. If nothing is mentioned explicitly. then what will be the moment of inertia?
2 by 5 mr square.
Very good. So in place of I can substitute
2 by 5 mr square.
yes. So 1 by 2 is there. In place of I am going to substitute 2 by 5 mr square. Is it clear to you?
Yes, sir.
Okay. So what gets cancelled? The 2 gets cancelled here. So you get 1 by 2 mv square plus 1 divided by 5 mr square omega square. Is it clear so far?
So far, sir. Yes.
Yes. Okay. So what is the relation connecting V and omega? Yesterday's lecture it is there. V is equal to R omega. Okay.
Yeah.
Yes, number.
Right.
You write that one?
So in place of V, I will write what?
R omega.
So
R.
V square will become.
Sorry, sir.
So V square will become.
R squared omega squared.
Yes. So now from both of these, I can take mr square common, right? Mr square omega square common. If I take LCM, I'll get 1 by 2 plus 1 by 5, right?
Right.
What is 1 by 2 plus 1 by 5? LCM is 10.
7 by 10. 7 by
5
10.
plus 2, 7.
7 by 10.
Yes. So 7 by 10 mr square omega square is the total kinetic energy.
Right.
So what is asked in this question? Not the total kinetic energy. What is asked? What fraction of the total energy is rotational, which means the ratio of rotational kinetic energy divided by total kinetic energy, correct?
Now we have total, we need to get rotation.
We don't need to get, we already have it. What is total kinetic energy?
7 by 10 mr squared omega squared.
Okay.
See here. The first part is what? Kinetic energy due to translational motion. What is the second part?
Rotational motion. Kinetic energy due to rotational motion.
Yes. So we already have it, right? So what is this part?
Half mr squared omega squared.
What is it?
Translation motion.
Kinetic energy due to translational motion, correct?
Right.
What is this part?
Kinetic energy due to rotational motion.
So do we need to separately find, or have we already
No.
found?
Already found.
Yes. So what should I substitute there?
So substitute 1 by 5 mr squared omega squared.
Very good. That's all. So mr square omega square cancels. So it is nothing but 1 by 5 divided by 7 by 10. Or I can write it as 1 by 5 into
2 by 7.
Yes. So the required ratio is 2 by 7, which is the first. So did you understand? Question on rolling. So whenever I say rolling, what does that mean?
Combination of translation and rotation motion.
So the total kinetic energy will be a sum of
Translation motion and rotational motion. Kinetic energy.
translational kinetic energy and rotational kinetic energy, correct?
Yes, sir.
Translational kinetic energy, you can use half mv square. For rotational kinetic energy, you need to use half I omega square. I you can calculate based on the shape of the moving object, right?
Right.
Suppose if it's a cylinder, then it will be half mr square. If it's a solid cylinder. If it's a solid sphere, it is 2 by 5 mr square. Suppose if it's a disc which is rotating, rolling down, it will be half mr square. If it is a ring, then it will be mr square. All right.
Right. Like
So
that.
accordingly, we will substitute and get this clear, Samuel.
Yes, sir.
Any doubts in this?
Understood, sir.
We should be move on to the next one.
Okay, sir.
Yeah, you have now made a note of all these.
Yes, sir.
Okay, good. Any doubts at this point?
No, sir.
No. Okay. Okay. So now I think we will discuss some concepts in oscillations, and we'll do a few questions on that also. Okay.
Yes. So just a minute.
Yeah, sure.
Okay, sir.
Okay, good. So let's go through this step by step, Samuel. A 3-meter long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall, as shown in the figure. Find the reaction forces of the wall and the floor. So the diagram is like this, right?
Right.
So you have this ladder. So your A to B is your ladder, correct?
Correct, sir.
So the ladder leans against the wall, correct?
Correct, sir.
So what is the mass of the ladder? 20 kg, correct?
Yes, sir.
So you consider the center of mass. So center of mass will be at the center of the ladder, correct? If there is uniform distribution of mass.
Hmm.
So let's consider this as the center of mass. And let me call it as D, okay?
Yes, sir.
Now you know that the weight, so the entire weight of the body, weight of that ladder can be assumed to be concentrated at that point, correct?
Correct, sir.
So obviously weight acts in the downward direction, correct?
Correct, sir.
W acts in the downward direction, point number 1, right? Point number 2, there are 2 contact forces. So the ladder is in contact. Consider this as a one-dimensional diagram. So the ladder is in contact at 2 different points, right? One is on the wall and the other one is on the floor, right?
Correct.
So this is on the wall. So you know that reaction force or normal reaction will be perpendicular to the surface of contact.
Correct, sir.
So here the surface of contact is the wall, correct?
Yes.
So your reaction force will be perpendicular to the surface. Is it clear?
Yes, sir.
So that we will call it as F1. Clear to you?
Yes, sir.
Now next. Next, what is happening here? The ladder is in contact at this point, right?
Yes, sir.
Correct. So it is going to be, the reaction is going to be perpendicular to the surface, right?
Yes, sir.
So N is going to represent what? The reaction force. Is that clear?
Yeah.
Okay. So what do we need to find? We need to find N as well as F1. Is that clear?
Yes, sir.
Any doubts still here?
No, sir.
Okay, good. So this distance is 3 meters. This distance is 1 meter, right?
Yes. Yes.
So the foot of the ladder is at a distance of 1 meter from the wall, correct?
Yes.
And the length of the ladder is 3 meters, correct?
Correct, sir. And
it's evident that this forms a right angle triangle, correct?
Yes.
So if I just draw it separately here.
Use Pythagoras theorem.
Yes, I can use Pythagoras theorem, right?
So you get root 8 to 2 root 2.
Exactly. So this will become 2 root 2.
2 meters.
Clear, Samuel?
Till there, clear, sir.
Yes, good. Now we need to apply the various. So this ladder is in equilibrium at this point.
Correct.
It is not sliding down, correct?
Right.
Yes, it is in equilibrium. It's
Correct.
given resting. It is resting. That means it is not moving, correct?
Correct.
So all the forces are balanced. That's what you need to understand.
Right, sir.
So the horizontal forces, balance the horizontal forces. The vertical forces are also balanced. Is it clear?
Yes.
Okay. So that's the first thing to note. So let's just read through what is given. So I'll tell you the first, the fundamental idea of how to solve this, right? You will apply two concepts. Concept number one, as I told you, the body is in translational equilibrium. Translational equilibrium means it is not moving in a straight line.
Right.
That means the force along the x-axis, the net force along the x-axis is 0, which means if there is any horizontal force in the right, towards right, it will be cancelled by the horizontal force towards
The left.
Similarly, the vertical forces, the net vertical force is 0, which means if there is any vertical force in the downward direction, it will be cancelled by the vertical force in the
Upward direction.
yes. Only then a body can be in translational equilibrium. Is that clear?
Yes, sir.
Equilibrium means that rest.
Where
In
it does
other
not.
words, net force is 0.
Right, sir.
Okay, great. This is the first part. Now with this, you will get two equations because you are doing sigma fx is 0. That means sum of all forces along x-axis is 0. You are also doing sigma fy is 0. Sum of all forces along the y-axis is 0. You may end up in a situation where you need third equation.
Right.
Because there will be 3 unknown variables. So if you have to find it, you will need third equation. So for finding the third unknown variable, you will need to use another condition, rotational equilibrium. The body is in rotational equilibrium. That means the body is not moving in a straight line and it is also not rotating. Clear?
Right, sir.
There are 3 points. Point number 1, or primarily 2 points. The body is in total equilibrium. What do you mean by total equilibrium? No translational motion, no rotational motion. Is it clear?
Right. Sir.
First, translational equilibrium. That means all the x direction forces are 0, all the y direction forces are 0.
Right.
With that, you get two equations. Third one, you can get it from rotational equilibrium being 0. That means the net torque is 0.
Right.
So that is a condition, right? So now let's move on and see how it is solved. So let's read through this. So this is the idea, Samuel, how to solve it. The ladder AB is 3 meters long, its foot is 1 meter from the wall. From Pythagoras theorem, its BC is 2√2. We already solved that. The forces on the ladder are its weight acting at its center of mass D. Reaction forces are F1 and F2 of the wall and the floor respectively. So this is F1 and probably this they have taken it as F2.
Right.
Okay. The force F1 is perpendicular to the wall since the wall is frictionless. So how is it now?
BF.
Perpendicular to the wall. Is it clear?
Yes.
Okay. Force F2 is resolved into two components, the normal reaction and the friction. Okay. See here if you see, they have mentioned that the wall does not have friction, right, Samuel?
Yes, sir.
But the floor might have, all right?
Correct.
So now tell me one thing. We have accounted for one of the forces, right? What is the force? We have accounted for the normal reaction, correct?
Correct, sir.
In general, don't you think this ladder will have a tendency to move in this direction? Slip.
Right.
Right? So that is nullified by
The force of friction.
the force of friction. Is it clear to you?
Yes, sir.
So your F2 is a resultant of F and normal reaction.
Right.
Your F2 is the resultant of normal reaction N and F, which is friction. Or in other words, you can say F2 can be resolved into two components, N and F. Does it make sense, Samuel?
Yes, sir.
So this is your F2. F2 is a resultant of what? N and
F.
F. Okay. All right. So F prevents the ladder from sliding away from the wall, is therefore directed towards the wall. That's also understood, right?
Yes, sir.
Frictional force should be towards the right. Any doubts in that?
No, sir.
Because ladder has a tendency to slide away, right, to the left.
Correct.
So friction should act in the opposite direction so that it nullifies that tendency of the ladder to move to the left. Correct?
Correct, sir.
Very good. Okay. So now we are clear about all the forces which are acting on the body, right?
Correct, sir.
Okay. Let's go to the solving part. So as I told you, in the vertical direction, say there are two things, right? One is what?
Translational equilibrium,
And the next one is what?
rotational equilibrium.
So in translational equilibrium, I told you two things, right?
Right.
In the vertical direction, there is no force, and also in the
Horizontal direction, no force.
no net force.
Net moment.
Correct, ma? Okay. Or in other words, the whatever force is acting upwards is balanced by the force acting downwards.
Right, sir.
Now just look into the diagram sample and tell me. If there is no net vertical force, what are the vertical forces here in this diagram?
N and F2.
No, F2 is not vertical. F2 is a
Okay.
inclined force. So
Okay.
F2 already we have resolved it as N and F. Therefore,
Right.
you don't have to consider F2. Go ahead.
Okay. The vertical forces.
Yeah. No, vertical means in Y direction. Upwards or downwards. That's all. Simple concept.
Okay.
So what are the forces which are acting upwards or downwards?
N is acting upwards.
N is acting upwards. What is acting downwards?
Down, W.
Yeah, for the entire system, I'm saying, right? So N is acting upwards, W is acting downwards. Because the system is in vertical equilibrium, N should be equal to W.
Right.
Are you understanding? So in the vertical direction, the net force is 0, which means N minus W should be 0.
Correct.
Or in other words, N must be equal to
W.
right. Similarly, horizontal forces. Can you tell me the horizontal forces which are acting?
F is there, force of friction,
Yes.
and F1.
And F. And they both must be
equal.
That's the second equation. Is it clear?
Right.
So the first equation is, come on.
N equals to W. Second equation is F is equal to F1.
So you got two equations, all right? So I told you we may be having three unknowns, so it's important that we get the third equation. Third equation, we cannot get it from translational equilibrium. We have to go for
rotational equilibrium.
Yes. So rotational equilibrium means the body is not rotating about any axis, correct?
Correct.
So you may take any axis and mention that the net torque is 0. Or torque is also called as moment of a force. Okay. This is the third equation, the most important, right?
Right.
Okay. Taking the moment of forces about any point. Actually, you can take it about any point. Okay. But in the question, it has been taken about the point A because I'll tell you at A, how many forces are acting, Samuel?
2.
Normal reaction and
Force of
friction.
friction. Yeah.
If you take A, then what will happen is the moment of the force about normal reaction and about friction will become 0. So it is common sense to take A.
Right.
You could also have taken D. You could also have taken B. Nothing wrong. Will you get the answer? Yes, you will get the answer.
Correct.
The smart thing is to take A because through A, how many forces are passing?
2.
2 forces. And any force passing through that point, above that point, if you're going to take
it becomes 0.
Torque, it becomes 0 because there is no distance between that force and that axis of rotation.
Correct.
For example, it is like this, right? Let's say you have a door. Let's say this is a door, okay?
Okay.
So this is your door. Now, So this is here you have the hinges, right?
Yes, sir.
Now you apply some torque, it'll open, right?
Correct.
And it'll close like so. So what motion it is undergoing?
Rotation motion.
Correct, right? So if I apply a particular force, accordingly, if I apply greater force, it'll rotate more, right?
Right, sir.
Suppose if I try applying a force here at the hinge, will the door rotate?
No.
No. Why? Because this is the axis of rotation. So
Yeah.
farther away from the axis of rotation I am, I'll be producing more torque.
The more easily it rotates also.
Exactly. So can I, if I try applying it at the hinge, at this point on the door, will it move?
No.
So that's the point, right? So your axis of rotation, if you take it as A, right? If you look at the example,
Mhm.
your normal force and the force of friction act along that line, right?
Right.
So it is like, you're applying the force at the hinge. Will it rotate?
No.
So rotational force is 0. So that's why it becomes 0, I'm saying. Did you understand?
Correct.
Because the perpendicular distance becomes 0. Okay, good. So now, so the torque due to normal reaction is 0, torque due to friction is 0. So this is gone completely. So torque exists only because of two forces. What are they?
N and F.
No, N and F is over, man. It's
Oh, yeah.
not there.
Okay. Okay.
The rotational force generated because of N and F is 0.
Oh, yeah. Sir.
Because I told you we are talking about point A, right?
Correct.
So there is no distance between point A and normal reaction or friction. They've passed through it.
Right, sir.
So I told you example, an analogy. It is like applying a force at the hinge of the door.
Correct.
It doesn't produce any rotation to the door. Is it clear?
Yes.
So what is gone from our equation?
N and F.
N and F is not going to figure out in our equation now. Understood?
Yes, sir.
So what is going to be the torque, the rotation effect is only going to be because of
O W.
W? What are the other forces acting on the body, on the system?
F1 is
The
there.
entire system, the four forces, right?
Yeah.
N, F, W, F1.
Yeah. So W and F1.
W and F1 only. Is that clear to you, first of all?
Yes.
Yeah. Now you have to calculate, how are you going to get the
Third equation.
equation, correct?
Right.
So is it clear? So you have taken N and F out of the rotational motion equation.
Yes, sir.
Right. Now we are in the last step of framing the equation. Because once the equation is framed, it's a piece of cake.
Yes, sir.
Right? Okay, good. I'm glad that you asked the doubt, right?
Right.
Good. So see here, observe carefully, Samuel.
Yes.
So now I'm just drawing it so that it's clear to you. So I'm drawing the point A here separately. This is the point. This is the axis of rotation. Okay, Samuel?
Okay. Yes.
Okay. Now, where is our W?
W is somewhere between the ladder.
Yes. So W is here, right?
Yeah.
This is W, correct?
Yes, sir.
So what is the distance of your point A from W? The perpendicular distance. This
Correct.
is the distance, correct, Samuel?
Yes, sir.
This we have to calculate.
Hmm.
All right?
Yes, sir.
Okay. Now can I say this total here, what is the hypotenuse? 3,
Three.
right?
3.
Correct. So this will be 1.5 and this will be what?
1.5.
Correct?
Yes, sir.
And will it be okay to consider that this 1 meter is also divided as 0.5, 0.5?
It is.
Yes, Samuel?
It is.
Okay. So now, can I take this distance to be 0.5?
Yes, sir.
Yes, very good.
Or I can take.
Yes, Samuel?
Yes, sir. Correct, sir. Yes.
Okay. So what is the torque? So torque is R times F,
Mhm.
as you already know, right?
R we have
So what is your R?
1/2.
1/2. Okay, ma'am? So 1/2 into W. Is that clear to you?
Yes, sir.
This is the torque produced by what?
W.
W. Okay, so this is one thing. Done. Correct?
Yes, sir.
Understood? Now the last one. What is the last one?
I need F1.
F. Correct? Okay. So F is acting in this direction. Is that clear?
Yes, sir.
This is your F1. This is your wall. Where is the point A?
Now is over. Point is at the bottom.
Point A is here, right? Now, can you tell me what is R? R is nothing but
1/2. Oh wait, the
wait,
1.5.
don't give an answer immediately without thinking.
Okay.
This distance is your R. Is that clear?
Right.
Perpendicular distance from the point A to that force. I am drawing it separately so that you can understand better.
Right.
Okay. So this distance is what we need to find. This distance will be your R for F1. Are you able to understand, Samuel?
Yes, sir.
From A, you have to drop a perpendicular to that force. Is that clear?
Correct. Yes.
So your W was here, you dropped a perpendicular from A, and you found the distance to be half, correct?
Correct.
So here, what are you doing? You are extending that force F1. From A, you are dropping a perpendicular. Is the concept clear to you?
Yes.
So your goal is to find what?
RF1.
Yes. So how do you find this R, right? Now let's do one thing. Let me extend this. Let me complete this, right, Samuel?
Yes, sir.
Is it not forming a rectangle, Samuel?
It is.
And won't the opposite sides be equal?
Right.
So I am interested in this distance, correct?
Correct.
And what is that distance? Is it not same as 2√2?
Yeah. So we have to.
Yes. So are you clear about this?
Yes, sir.
So what is your RF1?
2√2.
Right. One second. So what is the torque produced by F1?
R there.
Yes.
R
What is R?
2√2.
Have you understood this?
Yes, sir.
Good. So you have two torques, right? One is
Yes.
2√2 F1, another one is what?
1/2 F W.
Right? And both these torques must be equal and opposite so that, the net torque becomes 0. Correct, Samuel?
Correct, sir.
Just have to equate them. So 2√2 F1 equals what?
1/2 W.
That's what is given by this equation. Clear, Samuel?
Yes, sir.
Yes, good. Rest is simple calculation. So we got these three equations. Any doubts in this so far?
No, sir.
No, right? Okay. So now how do you do this? We just need to find two things, right? We need to find F1 and N, that's all. Correct?
Yeah.
Okay. So fine. So we need to solve. So when we solve, right? What is your N? N is nothing but W.
Yes.
What is W? Mass into gravity. What is mass?
Huh?
How much is the mass of the ladder?
20 kg.
20 into 9.8, correct?
Right.
So that will give you what? 196 Newton.
Correct, sir.
So you got normal reaction over,
Correct, sir.
correct? Then we want to find F1, right?
Yeah.
So what is F1 from this formula?
W by 4√2.
W by 4√2. What is your
Because
W?
2√2 into 2, that's it.
You know?
2√2 into 2 is 4√2.
That's what, that's 4, correct. So what is W?
196 Newton.
Yes, very good. 196 divided by 4.
4√2.
That's all right. So that gives you.
34.6.
So you got F1, you got your N over.
Yeah.
Fine. You have to find the net reaction force. Or let's say F2. F2 is the combination
Resultant
of
of
friction,
FNN.
right?
Yes, sir. Resultant of FNN.
Yes. So you have to find friction now. You have found through two forces. What are the forces you found? You found N, you found F1. You will also find friction, correct? Or F2.
Yes, sir.
What is F2? F2 it is a combination of what? Normal reaction and friction, correct?
Yes, sir.
So F2 is equal to root of F square plus N square.
Right. What is it?
But your friction is equal to F1 because we have already got that, right? F is equal to F1.
Mm-hmm.
So your F1 is what? 34.6 or your F is 34.6. You can substitute that.
So we can take it as 35 also, right? 34.6.
Oh, yeah. In CBSE, you don't have calculator, right? So it's okay. So I get the logic. That should be good. Okay.
Okay, sir.
Yeah. So F square plus N square. Why is it? Because
The resultant of these two forces.
because your friction is here, normal reaction is here. If you complete the rectangle, we know that the resultant is along the diagonal, right? Of the parallelogram.
Yes, sir.
Here the parallelogram is also a rectangle because the angle here is 90 degrees between friction and normal reaction, correct?
Yes, sir.
So this is your resultant force F2. So if you see, if this is N, this is also N. So F2 will be equal to Pythagoras theorem. F2 square will be equal to N square plus F square, or F2 is equal to root of F square plus N square. Got it?
Yes, sir.
Clear, Samuel?
Yes, sir.
So your F is 34.6. Your N is 196. So when you square it, you are going to get approximately 200 Newton.
Yes, sir.
So if F2 makes an angle alpha with the horizontal, you can also find that.
Yes, sir.
Your tan alpha will be what?
N by F.
Opposite by hypotenuse. What is opposite here?
N.
And hypotenuse is
F2.
F2. That's all. So N by F2. When you find, you get it as 4 root 2. So alpha will be tan inverse of 4 root 2. If you are given the natural tan log worksheet, you'll be able to find that it is 80 degrees. Otherwise, it's enough to stop it here.
Okay, sir.
So did you understand the whole process, Samuel?
Yes, sir.
So the idea is very simple. The idea is just using 3 equations. One is net horizontal force is 0. Next is what? Net vertical force is 0. They are no big deal. Very simple. The third one, you have to watch out and do it. What is third one? Rotational forces
0.
0. For that, what you need to do, preferably pick up a point where more forces are acting.
Right.
And make that as the reference point so that the torque due to those forces will become 0.
Yes, sir.
Then torque will be only because of the other forces. For finding out the R distance between that R, how do you do? Extend those forces from that point, draw perpendicular.
Yes, sir.
And find the distance from the given geometry or given data.
Yes, sir.
Is it clear, Samuel? It's a very interesting question. And something which makes you understand the logic and concepts.
Yes, sir.
So any doubts in this? Is it clear?
No, sir.
Sure?
Sure, sir.
Very good. Okay. Any other doubt, Samuel?
No, sir. This is only one.
Very good. Very good. Yeah. Go through the rest of the chapter also today, and let me know if you have any doubts.
Okay, sir.
Okay, good. So we'll move on to the next chapter now. Good job, Samuel. So you have prepared, and also you've also identified a doubt and asked. That's fabulous. Okay. Oscillations, right? So what is an oscillatory motion? We have seen what is a rotatory motion, correct?
Yes, sir.
Right? We have seen what is translatory motion. What is translatory motion?
So otherwise called as when the body only slides down.
Not slides down, moves in a straight line.
A straight line, yeah. Moves in a straight line.
All right. Okay. That's a translatory motion. When a body is going to move in such a way, or it's going to rotate about an axis, then it is called what?
Rotational motion.
Or in other words, all the particles in that body undergo circular motion.
Yeah.
When a body undergoes rotational motion, all the particles constituting the body, each particle undergoes what motion? Circular motion.
Circular motion.
All right. Such motion is called rotational motion. What is an oscillatory motion? A
Is
to
the
and fro motion is called oscillatory motion.
what's that?
To and fro motion.
Okay.
Write it down, Sam.
A to and fro motion is called oscillatory motion. Okay. Now let's go a little deeper. What kind of force will generate a oscillatory motion? Let us see. See, we have seen. Samuel, we have seen in the previous case, right? Previous chapters. What kind of force causes translatory motion, right?
Yes, sir.
If a body is already having a uniform velocity, then there is no force required, correct? To keep it going with that velocity.
Right, sir.
Right? That's law of inertia, correct?
Yes, sir.
Now, otherwise, if a body is at rest, then you'll have to apply some force. There will be acceleration. Because of acceleration, there will be change in velocity. The body is set into motion, correct?
Yes, sir.
Yeah. So a force, what kind of force is required? We have already seen. The force can create a uniform accelerated motion or non-uniform accelerated motion, correct?
Correct, sir.
For uniform motion, there is no force.
Right.
That means velocity is constant, then there is no force. Acceleration is zero.
Yes.
But if I have a force which is constant, then acceleration will be constant. It creates a uniform accelerated motion. The velocity will keep increasing or decreasing depending on the acceleration is, positive or negative.
Yes, sir.
Or it's a accelerated motion or decelerated motion.
Yes, sir.
If the force is dependent on time, then acceleration will also be dependent on time. In that case, acceleration is not a constant.
Right.
Okay. If acceleration is not a constant, then this motion is called non-uniform accelerated motion.
Right.
So pretty much understand, what kind of force creates a linear motion and what kind of force will create in linear motion, uniform, non-uniform accelerated, all that, right?
Yes, sir.
And we also understood recently that in this chapter, rotational motion, what kind of torque generates rotational motion, correct?
Yes, sir.
Torque is, as you know, product of your force and your
F.
distance, right?
Distances.
Yes. If you want to focus on your force, right? But there are other formula. Torque is your I alpha also. Torque is also can be written as dl by dt. All that also should be in your mind, right?
Yes.
Yes, sir. Okay. Now, if you see, we recently saw, right? If the force is passing through the axis of rotation, then the torque is zero.
Right.
Right? We were talking about the point A. About that point, if I consider the rotation of the body, due to the normal reaction and friction, what was the torque? Zero.
Right.
Because they both were passing through that point, correct?
Correct, sir.
Only if there is a distance of that point from the force, then there will be torque, correct?
Correct, sir.
So we also understand what kind of forces generate torque or rotational motion, correct?
Yes, sir.
And if a body is going to rotate with a constant angular velocity, no torque is required.
Yes, sir.
It's rotational inertia, right?
Right.
Similarly, if a body is moving with a uniform motion or uniform velocity, no external force is required.
Right, sir.
Similarly, if a body is already rotating with a constant angular velocity, no external torque is required, correct? Yes?
Yes, sir.
Okay. Now we talk about what kind of force is going to produce oscillatory motion, what kind of force will not produce oscillatory motion. Clear, Samuel? That's what we're going to see now.
Okay, sir.
So consider a force of the form F is equal to minus K x to the power n. Let's consider a force of the form F is equal to minus K x power n and analyze, okay? Let's say this is y-axis. Let's say this is x-axis. Now, let's consider two cases, okay? Case number one. I'll consider F is equal to minus K x square. We have to check whether this kind of force, if it acts on a particle, whether it will produce oscillatory motion or not. Okay,
Right.
fine. So now, where K is a positive constant, I can call it as a force constant. And x refers to the position of that particle along on the x-axis. F is the force. Okay. Now, okay, now tell me, let us say a particle is at a distance of x is equal to, at a position x equal to 4 meters. Can you tell me what will be the force experienced by this particle because of this? I'm applying a force of F is equal to minus Kx square.
Minus
What will be the force
16.
experienced at that point?
Sir, K is a constant, right?
K is a constant.
So we can take it to be 0 or something. Any value.
Any value other than 0, brother.
Ah, yeah. That's it. So x squared is 16. 4
Yes.
squared 16. And if we take K as what will be minus 16.
Minus 16K itself, you keep K as K.
Okay. Yeah.
Okay, it's a positive constant. Very good. Minus 16K Newton is going to be acting on this particle. What is the significance of minus sign?
Which means it's in the negative force.
Opposite direction, negative direction. All right, or negative x-axis direction.
Right.
All right, Sam. So if you want to make it more clear, you can also write an I cap here. That makes it very clear.
Right.
That means it is along the negative
Direction.
axis. Clear.
Negative
So what
axis.
will happen? This particle will now undergo. It will start. Suppose if it was initially at rest, now it will start moving to the left. Is that clear?
Yes, sir.
Because the force is acting in which direction?
In the opposite direction. It's because it's
Like
negative.
this, in along the negative x-axis. Is that clear to you?
Yes, sir.
Okay. Now, let's say the particle moves and it comes to a point where x is 2 now. What is going to be your F?
4 minus 4K.
Right now.
Minus 4K I cap.
Good. So still the force is in which direction?
The left direction.
So the particle will continue to move in the left direction, right?
Right.
Now let's say it comes to the point x equal to 0. Now what is your force at this point?
0.
0, right? So force is 0, acceleration is 0. Does the particle stop at this point?
Yes.
No, your particle won't stop if your force becomes 0. Because it has its kinetic energy, right? It has gained kinetic energy so far, right?
Yeah.
It doesn't become 0 instantly, yes or no?
Yes, sir.
Just because your applied force is 0, the velocity is not 0, right?
Right.
Only when the velocity becomes 0, the particle stops, correct?
Right. But it's still continuing.
Yeah, so it will still continue along the same direction, correct?
Yeah.
Now let's say it moves and it reaches the point x equal to 2. I'm sorry, minus 2. Now what will be the force? Tell me, Sam.
Minus plus 4K.
Is it plus 4K? Can you substitute and tell me? F is equal
No,
to
sorry.
minus K into minus 2 the whole square. So how much is it?
Minus 4K.
Yeah, it is still minus 4K I cap. So which direction is the force, Samuel?
Sorry for what?
Which direction is the
left.
force?
It's still moving towards the left.
Yeah, the force is in the negative direction. So it moves in this direction. Now let's say it moves to a point x equal to minus 4. Now what is the force?
Minus 16K I cap.
So which direction is the force?
Again in the left direction.
So my question was whether this force will produce oscillation, right?
Right.
Answer, what is the answer?
No.
This force will not produce oscillation, right? I have written a no here, correct?
Right.
Why do I say so? Because the
Only
force is only in one direction, correct? Whether particle is in the positive side of x-axis or negative side of x-axis, the force doesn't change direction, correct?
Correct, sir.
So there is no scope of the particle coming back.
Correct.
Oscillatory motion means what? To and fro, right?
Yeah, but it's only moving in one direction.
Therefore, there is no scope of it coming back. Therefore, this force F is equal to minus kx square will not produce.
Oscillatory motion.
Exactly. Now let's look at case 2. Okay. Any doubts in this sample?
No, sir, this is where it only moves in one direction, right? This force.
Exactly. Exactly. This force can create a one-dimensional motion. That's all.
Yes, sir. Clear, sir.
This cannot create a oscillatory motion. Correct?
Yes, sir. All clear.
So now let me consider the case. Once again, the force is of the form F is equal to minus kx power n. Same form.
Right.
But this time, it is not F is equal to minus kx square, but if it is what? F is equal to
Minus kx power 1.
1, not 2, right? And of course, for better understanding, I'm writing I cap. Okay.
Right.
So this is your y-axis. This is your x-axis. Now particle is once again at x is equal to 4, let's say. Now can you tell me what is the force acting on this particle?
Minus 4k I cap.
Yes, minus 4k I cap. So
And
particle
this
will
will
once again,
move
be
to the left.
accelerated towards the left, correct?
Right.
It will start moving towards the left. Let's say it reaches a position x is equal to 2. Now what will be the force?
Minus 2k I cap.
This should be, yeah, minus 2k I cap. Once again, which direction is the force?
In the left direction.
Let's say the particle reaches x equal to 0. Now what will be the force?
0.
0. What is the acceleration?
0.
Does the particle stop?
No.
No, very good.
Because velocity is still not 0.
Yes. So it has gained kinetic energy, that doesn't become 0 instantly. So because of that kinetic energy, it moves to the left. Let's say it moves to the left and reaches the point x equal to minus 2. Now what is the force now?
2k I cap.
F becomes equal to what?
2k I cap. Plus 2k I cap.
Very good sample. So force is in which direction sample now?
Now it's moving towards the right.
Yeah. So when the particle was to the right of x-axis, right? Right of y-axis, which means positive x-axis. The force was acting in which direction?
In the opposite direction. This is
To the left, correct? But when
right.
the particle has come to the left now, force has changed its direction and acting towards the
Right.
right. So what will happen? The particle may still move to the left, but it is opposed by the force for the first time.
Right.
So what will happen? The velocity will keep decreasing.
Correct.
So let us say the velocity becomes 0 at x equal to minus 4. Then it will not move any further, right?
F is equal to 4k I cap.
If it's equal to 4k I cap, no doubt about it, correct?
Yeah.
What I'm saying is, suppose when it reaches the point x equal to 4, the velocity becomes 0, let's say. Because why is the velocity becoming 0 now?
It stops. It's at rest.
No, why is it stopping?
Because it's being opposed by that force.
Yeah, it's being opposed. Exactly, right? So it stops at this point. Then after it stops, what happens? The force is still acting towards the right, so it will start now moving towards the
Right.
yes.
So it is an oscillatory motion.
Yeah, this will produce oscillatory motion. Is that clear now?
Yes, sir.
Once again, it moves to the right of y-axis. What will happen?
Sorry, sir. What?
No. Now this yellow line represents, the particle moving back, right?
Right. Yeah.
The moment it crosses to the right of y-axis, which means positive x-axis, then what will happen to the direction of the force?
We'll come this side again.
No, when the particle comes to the right, the force will once again be what? To the left. Correct? So it will again slow down. Then again, let's say at this point, the particle's velocity becomes 0. Once again, it starts turning to the left and moving this way.
To and fro, same motion.
So are you getting to and fro motion?
Yes.
Yes. Therefore, this force produces oscillatory motion. Is it clear?
Yes. Excuse me, sir.
Yeah.
So what's the significance of the plus sign?
Which plus sign?
No, F is equal to plus 2K, right?
It
I'm
has
asking-
changed the direction. It has changed the direction, right?
Okay.
So in the previous case, the direction was not changed, correct?
Right.
Yeah. So not only this force, if you analyze carefully, a force F is equal to minus kx, of course, produces oscillatory motion.
Hmm.
Similarly, a force F is equal to minus kx cube will also produce oscillatory motion.
Yeah.
Similarly, a force F is equal to minus k x power 5 will also produce oscillatory motion, and so on. Do you agree?
Yes.
Because in all these cases, the moment x goes to the negative value, F will change its sign. Do you agree?
Yeah.
So all these will produce oscillatory motion. Do you agree?
I agree, sir.
And mathematically you understand because the power is odd, right?
So that's why it produces.
Correct, correct. When the power is even, whether x is positive or negative, it retains same direction, correct?
Yes.
Now, among all these oscillatory motion, the simplest one is called simple harmonic motion. It is produced by this force. Among all oscillatory motions, the simplest is called as what?
Simple harmonic motion.
And that is produced by which force?
F is equal to minus kx to power 1.
Exactly. Is this clear to you so far?
Yes.
Okay. Now we come to SHM. So now we talk about simple harmonic motion. So here simple harmonic motion is an oscillatory motion, or you can say the simplest of oscillatory motions, produced by the force. What is the force which produces simple harmonic motion?
F is equal to minus kx.
That's all. Correct? F is equal to minus kx cube, F is equal to minus kx power 5, F is equal to minus kx power 7. All these produce oscillations. But the simplest of them is what? F is equal to,
Minus kx.
and that is called what motion?
Simple harmonic motion.
Yes, clear.
Yes.
Good. Now, from Newton's second law, we know that F is equal to what?
MA.
Mass into acceleration. So what is your acceleration?
Minus k by m into x.
This is the characteristic, or this is the way we define simple harmonic motion. So how do you define simple harmonic motion? A motion in which acceleration of the particle is directly proportional to negative of displacement. How do you define SHM?
Motion of it.
Motion in such a way that its acceleration is directly proportional to negative of displacement. Such a motion is called simple harmonic motion. Is that clear?
Yes.
Yes. Okay. Now let me consider a displacement. Let's say a particle is having a displacement x is equal to a sine omega t. Check whether this motion is simple harmonic motion, whether the particle is undergoing simple harmonic motion or not. If its displacement is given by a sine omega t, what should you check for?
Simple harmonic motion. It's
Whether acceleration is directly proportional to negative of displacement or not.
correct.
Correct? So you are given displacement, how to find acceleration?
Sorry, sir. I didn't hear. Could you
Tell
repeat?
me, ma'am.
Could you repeat again, sir?
If I give you the displacement, I've given you the displacement. I've asked you to check whether this represents simple harmonic motion or not. And you know what you need to do for checking whether it's simple harmonic or not. If the acceleration of the particle is directly proportional to negative of displacement, then it is simple harmonic. If it is not so, then it is not simple harmonic, correct?
Yeah.
So my question is, how do you find acceleration? You are given the displacement, how do you find acceleration? You've learned it, right?
ds by dt.
Yeah, good. So you will find dx by dt. If you find dx by dt, what do you get, Samuel?
You get acceleration.
You don't get acceleration.
Sorry. Okay, dx by dt.
What is dx by dt? What is x? X is displacement, right? What is dx by dt? Come on, Samuel.
Velocity.
Very good. Rate of change of displacement with respect to time is velocity, correct? Good. Then what should you do?
Then differentiate further to get acceleration.
Differentiate further, right? That means you will differentiate the velocity.
dv by dt equals to a.
Very good, very excellent. That's all. So now if that a, whatever you find, if it is proportional to minus of x, then you can definitely say that this motion represented by x is equal to a sin omega t is definitely simple harmonic, correct?
Yes.
Okay, now you need to, your knowledge and differentiation is tested. What is the differentiation of sin x?
Cos x.
Yes. What is the differentiation of 5 sin x?
5 cos x.
Good. What is the differentiation of 5 sin 2x?
Sin 2x is 2 sin x cos x.
That doesn't help. Or maybe I'll put. Okay. What is the differentiation of 5 sin 100x? Okay, well, let me.
20x, sin 20x.
What 20? Right?
20.
Think and do it. I did so teach you.
Okay, so this is solved using chain rule. Okay. Anyways, just observe what you should do. See, listen, no? Observe the board.
Using.
So it's a function of function, all right? So normally if I had simply given 5 sin x, what would be the answer?
5 cos x.
So 5 sin whatever x, right? I have given 5 sin 100x. So don't worry about the 100x for the time being.
Okay.
Sin function, if you differentiate, what you will get?
Cos.
So you directly write what? 5
Cos.
cos. What is the angle?
100.
100x, correct?
5 cos 100x.
Write it as it is. But that's not the sum. Sum is not over, okay?
Right. Okay.
Now you look into the second arrow which I mentioned. Now you should zoom into the inner function.
The constant. 100.
Inner function is 100x. If you differentiate it, what do you get, Samuel?
100.
That you should multiply. So your answer will be
5 cos.
not 5.
Sorry, 500
For this
cos.
100, you should not multiply with the angle, okay?
Yeah.
Did you understand?
Yes.
This is indeed the answer.
So you should only multiply to the cos part or whatever is given. Like now we have 5 cos, right, sir?
Yeah.
So that part only you should multiply by 100.
This is a number. The number you cannot multiply with an angle, okay? This 30 degrees.
Right.
Will you multiply a number with an angle?
Right. You can't.
What is sin 2x into? If I'm multiplying sin 2x with 4, what do you do? What is it? I hope you don't say sin 8x.
No. Not sin 80.
It is 4 sin 2x. Understood?
Right.
This is called chain rule. Okay. So why is this important? This is important for us to do this sum.
Right.
And chain rule is like the heart. Okay. So if you understand chain rule properly, entire differentiation will become easier.
Yes, sir.
Okay. Now let's see. Now just going by this logic. If I'm going to differentiate A sine omega t, consider it like what? 5 cos 2x. Can you tell me the answer for 5 cos 2x differentiation?
I have not done it.
Or 5 sine, okay, 5 sine 2x. Let's make it simple. I have 5 sine 2x. What is the differentiation of 5 sine 2x?
10 cos 2x.
Exactly. 10 cos 2x. Very good. Are you clear, Samuel?
Yes.
So 5 is constant. Sine 2x, if you different sine of anything you differentiate, what do you get?
Cos.
Cos of the same thing. So you write cos of 2x.
Into
It's
2.
not over it.
Yeah.
Part you have completed. Now 2x, if you differentiate, what do you get?
2.
So this
So it will be 10 cos 2x. 10 cos 2x.
very good, very good. Excellent. Now apply the same logic here. Your A is like this number 5. Your omega here is like that number 2. Your T is like your X. Now tell me what will you get if you differentiate A sine omega t?
A cos omega into omega t.
A cos omega t. Okay. This whole thing into omega. You said A cos omega into omega t. What is it? A cos omega t into what?
Into omega.
Is that clear to you?
Yeah.
So first sine function. So when you differentiate, you get cos. Then omega t is like the 2x. Omega is a constant. So 2x when you differentiate, you get 2. So like that, omega t when you differentiate, what do you get?
Omega.
Yeah. So how do you write it?
A cos A omega cos omega t.
Is that clear to you?
Yes.
Now we'll come back. Okay. We come back to this question. So when you differentiate A sine omega t, what do you get?
A omega cos omega t.
Very good.
Now we need acceleration.
Very good. That means we have to differentiate once again.
Yes.
So now tell me this.
A omega cos omega.
You differentiate that. Tell me what will you get if you differentiate that?
Cos everything is cos is minus sign. We have to take the minus sign out. So sin omega t differentiation into omega. I'm getting minus a into omega sin omega t into omega.
Very good. Very good. What should you do to that final omega which you got?
Sorry, someone.
You're right. So what do you get? Minus a omega sin omega t into omega, right?
Right.
What do you do with that omega which you got it to the last?
Multiply.
Now tell me, I have to multiply, what do you get?
Minus a omega squared. Then sin omega t into omega.
Hey, you have already, how many times will you multiply omega?
Okay. Okay, omega squared sin omega t omega.
Why are you retaining that omega, man? I don't understand. See here, 5 cos 100x into 100. This 100 you multiply with 5 and say 500 cos 100x, right? Why do you keep saying that 100 again? A sin omega t, if you differentiate, you get A omega cos omega t. Do you keep telling that omega again and again and again?
No.
Now tell me correctly. What is it?
Minus a omega squared sin omega t.
That's it, right? Okay, good. So are you clear, Samuel? Any doubts?
No.
Okay, good. So minus a omega square sin omega t. Clear? 100% clear?
Yes.
Okay, good. Now, compare it with the question and see, what is this? What is a sin omega t?
Displacement.
Hmm?
What is a sin omega t?
Hmm.
Displacement.
Yeah, very good, very good. So a sin
The
omega t is
negative part
x,
of it.
nothing but x, correct?
And they've got the negative part also.
Very good, very good,
So it is in SHM.
very good, very good, very good. So a is equal to, come on, minus
K into or minus omega squared x.
correct?
Right.
Basically, we have got a is directly proportional to what?
Minus x.
Therefore, as you rightly said, it is what?
Is in SHM.
Good. So did you understand the whole logic?
Yes, sir.
Okay. Now here we saw a is equal to minus k by mx, correct?
Hmm.
Here we got a is equal to minus omega square x, correct?
Yes, sir.
So can I say minus k by m is same as minus omega square?
Yes, sir.
Very good. So minus k by m is equal to what?
Minus omega squared.
So minus gets cancelled. So what is omega square? K by m, correct?
Yes, sir.
So what is omega?
Root over k by m.
Right. Important. And how can I write omega? We have seen, recently we have seen, in terms of time period.
Hmm.
How can you write omega in terms of time period?
D theta by dt.
That's correct. But in terms of time period, I'm not asking in terms of angular displacement.
Oh.
We just saw, right? Earth shrinks to half its size. In that sum, did we not use omega is equal to 2 pi by t?
Okay.
Okay, so I'm going to use omega is equal to 2 pi by t. So can I say 2 pi by t is equal to root of k by m?
Right.
So take reciprocal. So what will be time period equal to?
Just a minute. Root over k by 2 pi m.
What? Just asking you to take reciprocal, right? So what is it? T by 2 pi is equal to root of m by k.
Ah.
Then just to take 2 pi that side. That's all. Time period is equal to 2 pi root of m by k. Clear?
Yes.
Yes, no?
Yes.
Have you noted down?
Yes.
Good. Any doubts in this so far?
No.
Okay, good. So now let's move on. Okay, now let's explore this, okay? So if I have a displacement equation of a particle given as x is equal to a sine omega t, right?
Right.
Then what is x called?
Displacement. Displacement.
Yeah, displacement of the particle. What is omega called?
Angular velocity.
It is called
Angular velocity or angular frequency.
Very good, very good. And how is it related to frequency? Omega is equal to 2 pi into f. What is f?
Frequency.
What do you mean by frequency? Frequency is defined as
Number of
what? Number of oscillations per second. Number of oscillations completed per second is called frequency. All right.
is
Omega can also be written as what?
2 pi f or
That's what we have written here.
yes, also.
What else in terms of time period? Quick. Now
2
tell me.
pi by t. 2 pi by t.
Good, good, good. Okay. So omega is equal to 2 pi by t. What is t called?
Time period.
Very good. Your t is called time period of the oscillation. What do you mean by time period of oscillation?
Sir, can be defined as where the oscillation repeats itself.
Oh, that is periodic, correct? That's fine.
Sorry,
What
where
is
the motion repeats itself.
Huh?
Where the motion repeats itself.
It's fine. What is time period?
Ah.
Time
Time.
taken to complete one oscillation. What is frequency? Number of
oscillations per second.
Time period is nothing but time taken to complete one oscillation.
Right. So does time period have a unit?
Obviously,
Time.
time taken. What is the time? Seconds, minutes, hours. SI unit is second. Okay. What is the unit for frequency?
Hertz.
It's very good. You've learned it in your lower class also, right? So anyways, what is the relationship between frequency and time period? They're just reciprocal of each other. You can see here, right? Omega is equal to 2 pi divided by t. You can see omega is equal to 2 pi into f. Both are same, right? Which means f is what?
1 by t. So yeah.
Frequency and time period are reciprocals of each other. Keep that in mind. Okay.
Yes.
Hertz, you can also write it as second inverse. Because it's 1 by time period, right?
Right.
So unit will be 1 by second. Understood?
Yeah.
Okay. So for time taken, it is second. Clear?
Yes.
SI unit. Okay. Now you understood everything about omega.
Yes.
Omega is angular velocity or angular frequency. How is it
Yes.
related to frequency? Omega is equal to 2 pi f. F is frequency. Frequency is nothing but number of oscillations per second.
Right.
Okay. And what is time period? Omega, how is it related to time period? Omega is equal to 2 pi by t.
Or
So
2
t
pi
is
f.
what? Time period, time taken to complete
One oscillation.
one oscillation. What is the relation between f and t? F is equal to 1 by t. Frequency is the reciprocal of time period. And vice versa. Time period is the reciprocal of frequency. Clear?
Yes.
Now let's move on to the next part, which is A. So A is called amplitude of the particle. Amplitude means maximum displacement. So what is A? A is called amplitude. What do you mean by amplitude?
Maximum displacement of the particle.
Yes. All right, Samuel. So why do I say it is maximum displacement? Because your x is displacement, correct?
Yes, sir.
X will be maximum when the right side is maximum, correct?
Yeah.
Look at the board, Samuel.
Okay.
Yeah. So right side will be maximum when sine function reaches maximum, correct?
Right.
What is the maximum value of sine x?
One.
1, correct?
One, yes.
So at that time when sine function reaches 1, x will be equal to a, correct?
Yes, sir.
So a is the maximum value of the displacement. Is that clear now?
Right.
What happens when sine function becomes 1?
Yeah.
So is this whole thing clear to you?
Yes, sir.
So the description of function x is equal to a sine omega t, correct?
Yes, sir.
Okay, good. Now, so a is called amplitude, omega is called angular frequency or velocity. It's related to f, it's related to time period, all this right?
Yes, sir.
Good. Now this will be important for while we solve the questions, right? Okay. Now let's look at what we did earlier. We'll come back. So we got, if the displacement equation is x is equal to a sine omega t, correct? Then what will be the velocity?
dx by dt.
What do you get? Come on, do it again and tell
A
me.
omega cos omega t. A
No.
omega cos omega t.
Okay. A omega cos omega t. Now we are going to get another expression for velocity. Okay.
Actually, one minute.
No. We are not going to get acceleration. The acceleration we already got it. I'm going to get another expression for velocity. Okay, ma?
Okay.
What is sine square theta plus cos square theta?
1.
So how can I write cos square theta?
1 minus sin square theta.
How can I write cos theta?
Root over 1 minus sin square theta.
That's what I'm going to write. So how can I write cos omega t?
1 minus sin squared omega t.
Yes. Right.
Yes.
I'm going to send this a inside, okay, inside the root.
Okay.
If I send it inside the root, don't you think it will become a square?
Right.
Because when I take it out of the root, a square, root of a square becomes what?
A.
Right? So if I send a inside the root, it becomes what?
A squared.
Yes. Already there is 1 minus sine square omega t. Is this understood?
Yes.
Okay. So I'm going to multiply this a square inside. So what would I get?
A squared minus A. A squared sin squared omega t.
Correct. Okay, now, so velocity becomes omega into root of a square minus. Can I write a square sine square omega t is what? A sine omega t the whole square?
Yes.
So from the question, can you tell me what is a sine omega t?
Sorry. Displacement x.
Yes, very good. So velocity is equal to omega into square root of. So can I write it as omega into root of a square minus x square?
Yes.
Yes. So that is the other equation.
Right.
Is it clear, Samuel?
Yes.
The other expression for velocity. Okay.
Okay.
And of course, what is my acceleration?
Minus A omega squared sin omega t.
Yeah, and that is nothing but minus omega square x. We had established that, right?
Yes.
So all this is clear with clear picture.
Yes.
Okay. Now, let's find out the energy associated in simple harmonic motion, correct? Of a particle undergoing simple harmonic motion, we'll find the energy associated. So have you noted this down, Samuel? Any doubts in this?
No, sir, all noted.
All noted down, right? Okay, now, energy possessed by a particle executing simple harmonic motion. Energy possessed by a particle undergoing simple harmonic motion. So the total energy possessed by a particle. Okay. So the total energy possessed by a particle undergoing simple harmonic motion is a sum of its kinetic energy and potential energy. Yes, Samuel?
Yes, sir.
Now you can understand, right? Swinging of a simple pendulum is a typical example of SHM. Of
Correct.
course, not linear SHM, angular SHM we call it.
Right.
Let's say we have a simple pendulum. Let's say I'm going to stretch it or pull it to the side by an angle theta. Then what is going to happen is a restoring force is going to be set up, correct?
Correct.
Because of that restoring force, what's going to happen is the pendulum is going to start swinging, correct?
Correct, sir.
So now the extreme corner is called extreme position. As you can see, the extreme position is at a height h from the ground, correct?
Yes, sir.
We consider this as height h. So what has happened? The particle has been elevated. Earlier, let's say the bob was here, okay? Now I have taken it here, right?
Yes, sir.
So what is happening? So the bob has gained some height, correct?
Correct, sir.
Gain some height means what?
It
Potential
means
energy has increased. Got it?
what, sir?
No. If a body gains height, potential energy increases, correct? Because potential energy is given by what? mgh,
Right.
right? So potential energy is maximum at the extreme position. And if you have seen the pendulum swinging, right?
Right.
At the extreme position, the velocity becomes zero. That's why it stops, correct?
Yes, sir.
It stops momentarily and changes the direction, correct?
Yes, sir.
So my height is maximum. Because of that, potential energy is maximum, but kinetic energy is zero.
Right, sir.
At the extreme position, what is the kinetic energy? Zero. Why is it zero? Because the pendulum stops momentarily at that point, correct or not?
Right, sir.
I don't know if you have seen, right? Earlier days they used to have, right? Wall clocks, if you see, the one which
Right.
pendulum clock. Have you seen by any chance? No.
Maybe only once, sir, not really.
Yeah. Okay. So it was a very common thing, in probably 20 years back.
Wow.
Okay, no problem. So see here. Now what you can see is as the bob is coming down, right? As this bob is coming down, its height is decreasing, correct?
Yes, sir.
As its height is decreasing, what will happen to its potential energy?
As the height is decreasing, it will also slowly starts becoming zero.
It's decreasing, correct? Very good.
And decreasing.
Now this potential energy is getting converted into kinetic energy, all right?
Right.
So it will appear as increase in velocity of the bob.
Right.
So the pendulum speed will increase. Are you understanding?
Yeah.
And when it crosses what we call as the mean position. So this position is called the mean position. All right.
Yes, sir.
When the bob is going to be here, when the pendulum is going to be here, this position is called what, Samuel?
Mean position.
Yeah. So at the mean position, can you tell me what is happening?
It suddenly stops. It crosses it.
It doesn't stop now.
Yeah, so it crosses.
Crosses it with maximum velocity. Why maximum velocity?
Because potential energy is getting converted to kinetic energy.
Ah, yes. And potential energy is 0 at this point, and kinetic energy is maximum. Is that clear?
Yes, sir.
So potential energy is minimum, whereas kinetic energy is maximum at this point.
Right.
And once again, it goes to the left extreme, and left extreme position also same story repeats. Potential energy becomes maximum, kinetic energy is 0. Clear?
Yes, sir.
So in tomorrow's session, we can derive the expression for potential energy. Right now, we will just do the kinetic energy and stop. Okay.
Okay, sir. Okay.
So what is kinetic energy? Kinetic energy is nothing but what?
Half mv squared.
Yes. So if the mass of the pendulum or the bob is m, it is undergoing simple harmonic motion. So I can use the equation which we have derived earlier. So what is velocity? Come on.
Velocity is omega cos omega t.
Yeah. So what will be my kinetic energy? Half m. Come on.
Please, a squared cos squared omega t.
A square omega square
Cos squared omega t squared.
omega t square.
No, omega t. Sorry.
What's kinetic energy?
The whole expression.
Is it clear, Samuel?
Yes, sir.
Is there any other way I can write kinetic energy expression? Yes.
P squared by 2f.
That's fine. But we know it is half mv square, correct? But what is v? Did we not derive another expression for v?
Yes.
What is it?
Omega into root of a squared minus x squared.
Yes. So we could substitute this as well. Both the expressions are important. Clear?
Yes, sir.
So this becomes equal to half m. When you square it, so it's omega square into the root is gone, so it becomes what?
A squared minus x squared.
This is another important expression for kinetic energy.
Right.
Take this down. Getting the potential energy requires a little bit little integration. So we'll do it in the next class, tomorrow's class. And then we can solve questions on oscillations. I think in about an hour or so, we'll be done with that. Then another hour, we can get into thermodynamics or thermal properties. We can discuss or kinetic theory of gases. We can just discuss that part.
Okay, sir.
Okay, Samuel. Any doubts in this, Samuel? Is this clear?
No, sir. So what about math, sir?
Do you want to start with math tomorrow? We can.
Okay,
How
sir.
much more is there in physics?
So
Tomorrow.
any doubts, Samuel, in what we discussed today?
No, sir.
Good.